Thanks everybody for coming to my presentation on context-agnostic actors. My name is Dmitry Sagatelyan. I'm a certified LabVIEW architect, a LabVIEW champion, and a regular presenter at NI Weeks, CLA summits, and now GLA summits. I'm using LabVIEW since 1998, which was version 5.0. Coming from a software engineering and computer science background, I'm passionate about bringing software engineering methods and best practices to the LabVIEW community and figuring out actor programming best practices in LabVIEW, and this presentation is about the latter. Over the years, I designed 4 actor frameworks, one of which use the command pattern like the NI actor framework, but I don't use NI actor framework. It's a matter of another presentation if you ask why. I also designed, I think, the first LabVIEW reuse library built from bottom up on the solid design principles, and I use it constantly on my projects. Back in 2009, I started a company called Artwork Technologies, and since then, I'm a full-time LabVIEW consultant in the San Francisco Bay Area. So today I would touch on the following. First, I'll cover several distributed application scenarios. Then we'll talk about what is a context-agnostic actor. It's a term I made up because I didn't find anything in the literature about this thing. A brief overview of 3 messaging patterns. Then I'll talk how to design a context-agnostic actor with details and code snippets. Talk briefly about the distributed message broker I am using, and go over a couple of examples of actual code at the very end. I would prefer taking questions at the end of the presentation because I'm kind of short on time, and you may find answers to your questions in the downstream slides, so I can hang out and answer your questions. It's hard for me to speak to the slides and look at the chat, so I beg your pardon if I don't see a question in time. Okay, there are 12 people, that's a good crowd. So let's start with the presentation. Distributed message, distributed application scenario number 1. You have an existing application, actor-based application that works, and you need to create a remote monitoring client for it. And the question is it possible to interact with the existing application without updating its code? The answer is yes, if the application is built on top of a distributed message broker. A similar scenario, slightly different. Is it possible to integrate an existing application into the enterprise without changes to its code? And again, the answer is yes, but instead of a remote monitoring client, you need to create an enterprise gateway that would take messages from the enterprise and messages from your application, convert them, and forward to the other end. That's an important scenario. Scenario number 2, you have a single application working in the same address space, in the same container, like an EXE or LabVIEW IDE, and you want to split it into 2 or more parts and make it distributed. Is it possible without changes to the actor code of the original application that is working? And again, the answer is yes. If your actors are context agnostic and they run on top of a distributed message broker. Third scenario, you have a distributed application split in several parts, and you want to temporarily move one or more actors from one application, from one part of the distributed application to another. Is it possible without changes to the actor code? And again, the answer is yes, if the actors in your application are context agnostic and run on top of a distributed message broker. The use cases for this scenario are rebalancing compute node loads, scaling distributed application throughput, and very important for developers, temporarily moving actors from RT nodes to PC to simplify testing and troubleshooting. Actor programming is built on top of the actor model of computation that was created by Professor Carl Hewitt of MIT Computer Science Lab back in 1975. It is based on three elements: the actors, which are the universal primitives of concurrent computation; messages, which are universal units of communication; and message carriers, which deliver messages between actors. And when an actor receives a message, it can concurrently send messages to addresses of other actors, create new actors, and designate how to handle the next message it receives, which in software engineering we call changing its state. However, literally following this model in software design violates some important software engineering best practices. And specifically, it violates the dependency inversion principle, which states that high-level modules should not depend on low-level modules, both should depend on abstraction. In this example, a scanner class or actor needs to call 3 devices to perform a sample scan. In the old days, we used to explicitly call methods on specific device drivers in the scanner code, but dependency inversion principle tells us not to do this. So the scanner development, scanner component development needs to create an API, a dependency interface for each of the devices, and make sure that specific device drivers implement those interfaces and call methods of such device drivers only through those interfaces, which in total would form a dependency interface for the scanner. This is one part and is the foundation of any plugin architecture. And in this case, this is a hardware abstraction layer that we all know. The other thing that dependency inversion principle tells us is that a top-level module should never create any of its subcomponents, because if it does, it gets statically coupled to specific type of that subcomponent. So that's another no-no, which I don't know how many of you try to avoid. So for actors, I can reformulate the dependency inversion principle as follows. An actor should not create other actors, and an actor should not directly establish connections to other actors. And by directly, I mean if it does, it would be coupled to the event handling mechanism of such a concrete actor, which again statically binds it to the actor type. So that's another thing you want to avoid. So we're here to define what context-agnostic actor is. And surprisingly, an actor is context agnostic if first, it does not create other actors, and second, it does not directly establish connections to other actors. So a context agnostic actor essentially is a result of observing dependency inversion principle when developing actor-based applications. And context agnostic actors enable using scenarios 1, 2, and 3, which I talked about before. So the question now is, how does an actor get its nested actors, and how does an actor know where to send its messages if it cannot connect to its nested actors. Enters dependency injection design pattern. This is a pattern that can be used on regular classes, by value classes, or on actors. And essentially what you need to do at the beginning of the project is to make a conscious decision to split your project code into two parts. The first part is all reusable objects that were specifically designed for this application or brought in for reuse from other applications. And the rest of the code, which is application specific and knows everything about the reusable objects. This is a smaller part of the code, the application specific code. Typically, it boils down to one class per application and probably constitutes 1.35% of the total application code, so it's really small. And its only function is to create reusable objects, instances of reusable classes, configure them, and pass them to one another to create the dependency, which is called injection. In actor-based systems, assembler class creates all application actors like regular classes, and it's also a good spot for interconnecting all application actors into the system. So if you're doing a distributed application, you need to have an assembler class for that application. Now let's briefly go over messaging design patterns. I'll give you a difference between the mediator pattern, event aggregator, and message broker. A mediator defines an object that controls how a set of objects interact. It is one of the 23 original Gang of 4 patterns. In this example, we have a control tower and the aircraft, and aircraft communicates with control tower, not with each other, and control tower imposes constraints on arriving and departing aircraft. So mediator promotes decoupling of the object in the application, thus it's solid friendly and it's a good thing to use. If you ever did an actor framework application that followed the tree messaging, strictly followed tree messaging, you probably had a hierarchy of mediator objects that had nested classes in them. The second messaging pattern is event aggregator. And the thing about it is that in software engineering, there is a separation of concern principle that tells us that a module should do only one thing. And the mediator object does two things. First, it enables exchanging messages, and second, it imposes policies on other actors. So if you strip off imposing the policies or business logic from the mediator object, it turns into an event aggregator. And its only concern is how to move messages from publishers to subscribers. And typically, an aggregator manages a set of topics which are used to transfer data, to push data from publishers to subscribers. And the good features of this pattern is that it decouples publishers and subscribers from each other. They don't depend on each other. They depend on topics that are part of the event aggregator class. It decouples topic lifetime from publishers and subscribers, a property extremely important in LabVIEW. And it supports one-to-one, one-to-many, and many-to-many message routing. It also allows publishers publishing and subscribing of messages to multiple topics, and it removes constraints on objects instantiation order. In case of actor-based system, it's actor instantiation, which is a kind of problem in a large system, but it's even a bigger problem in a large distributed system. So event aggregators are good things. The third pattern is the message broker. A message broker is concerned with connecting incompatible or independently designed subsystems. With the event aggregator, publisher and subscriber had to understand messages sent to each other. It is the responsibility of the developer to make sure they do understand each other's message. A message broker is concerned with translating messages that are created by a publisher that wasn't designed to communicate with a subscriber. And the message broker essentially has two parts. First, it translates a message. And the second, it routes that message through a nested event aggregator to all the subscribers. And since there may be many subscribers to a single topic, the translation, optional translation, should happen on a per subscription basis. This is very important. Message translation is a generic term, and it may include like substituting one message for another. This one issues a double message, and this one may be designed to get its string representation. So you need to substitute a double binary message into a string for this subscriber. It can translate messages format like XML to JSON, vice versa. It can filter messages by subject if subscribers are only interested in a subset of messages coming from a publisher or a topic, and can reduce message rates because, well, you don't need, when building a UI, you don't need to get RPM values from an engine at 50 Hertz. It's enough to get messages only when values of the RPM values change enough, like 1% or more, in order to display the actual change. And for sensitive data payloads, you can encrypt messages during their translation. So the challenge here is how and where do you perform message translation without altering your existing actor code? Is it possible at all? And the answer is yes. Of course, it is possible if you do it the right way. So I built a message broker over the years, and I presented it a couple of times. Here, I'll just refresh what I've been talking in the other presentations. A message broker is built around 4 classes. You have the message abstract class. You have a message transport abstract class, which is used to shuttle messages between actors. You have a message broker interface, which is used by actors to subscribe, unsubscribe, register to publish, and unregister to publish to certain topics. And you have message filters, which are an optional feature of subscription that allow you to do message translation. It is easy to create new types of actor messages for an actor and send them to other actors. And it is easy to create new message transport and subscribe to using the message transport your actor uses to receive messages. Now, the top part doesn't have an implementation. Implementation is here, the orange part. And thing here is the way I did it. A message broker is not an actor, and it does not forward messages itself. It only It only keeps track of all the topics created, and it needs to be accessed by multiple actors at the same time. So it has to be a by reference class object. And in order for it to be by reference class object, you need to create a GVR-based interface, which calls into this implementation. And this GVR-based interface needs to implement the message broker interface. So that's pretty much it, how it works. And all of your actors are decoupled from a specific implementation of a message broker through the abstract message broker interface class. Now, how would an actor send and receive messages with this design? First of all, let's look at the private data of one of the actors. It has configuration settings that I load, for example, from my .ini file. It has the message broker interface object here. That's how you subscribe and unsubscribe from topics. And it has data transport objects for all topics that it subscribes to and all topics it publishes to. And since this actor has a UI, you see it uses event structure, it needs also the event registrations to be able to get messages from the billboard and from data inputs. Turns also that this actor has two worker loops, one producer and one consumer, and it holds the message transport objects for sending messages to the worker loops. And to send a message, your actor would do the following. First, it needs to create a message itself. This is a Boolean value change event. So it needs to create a Boolean message. It selects the label of the control as the subject, creates a message, and then sends this message to the data out message transport through data out message transport. That's how you send it. Then you log the message to your local log, and if there were any errors in this sequence of execution, it would log an error to the global log. And after that, it would send the command to a producer worker loop, and the command would be either disabled or enabled. So lots of action packed in a small area of your code. To receive a message, you need to do the following. You get a message on the data in. See this data in event reference. You get the subject of that message. If it's Boolean 1 or Boolean 2, you know it's a Boolean by design. So you convert it to a binary Boolean message. Then you use your accessor method to get out the subject and the payload, the Boolean value. You branch on whether it's Boolean 1 or Boolean 2 and perform whatever actions you need to perform on this message. So this is pretty straightforward and it's easy to do. I use this architecture, I use this message broker since 2015. It scales well, etc., etc. So let's talk about how you connect actor-agnostic, context-agnostic actors into a system. For every distributed system, your design document needs to list all the actors and all the messages it can send to other actors or publish to certain topics, which constitute the data bus. Here I have 5 topics, 3 actors that can communicate between themselves or send messages to themselves. and one of the actors has a producer and a consumer loop, but producer doesn't send messages to actor B. It publishes those messages to topic C, and consumer takes messages from topic A. This is quite an elaborate messaging topology. So the question is how you translate this messaging tree into the data transport objects that reside in individual actors' private data. And at the same time, keeps actor objects decoupled from each other. And this is what I'm gonna cover right now. If you remember, we have an assembler class that brings up the entire system. And the system you start bringing on the entire system by passing it a list of actors and a list of topic names, actor names and topic names. And as the first step, the bring up method creates a message broker instance, easy, and then it creates all the topics listed in the data topic list. Not much really. The second step would be creating all actors and interconnecting them together. And this diagram encapsulates all those actions. Well, actually, these two diagrams. So what we do here, first, we create the three actors. This is the main GUI. This is actor A, and this is actor B. We pass them the names we specified, and they are created, but they didn't start yet. It's just a by value object right now. The next thing you do is you interconnect those objects using a mapping from application scope names. These are application scope names into actor scope names. In the application scope, the main GUI knows it has actor A and actor B, and it has billboard and a bunch of topics, but actor A was designed knowing that it has data in message transport and data out message transport. These names are different from this, so you need to map them. And this is done right here. You just assign appropriate names from the data topic list to those actor scoped names. And then for each of the actors, you call an open communication method, open connection method, which does the following. This is for actor B, which has the two worker loops. You split your topic names into publishers and subscribers and create them separately. Since this is a event structure, you need to create the event references. Then you can explicitly create message transports for your worker loops and write everything into the private data of actor B. And you need to do this for actor B, for actor A, and for the main GUI actor. So this is pretty much it. We had specified a very elaborate messaging topology, and you can create it just like this, quick and simple. Okay. Whatever I was covering before is like a local message broker. It could work only within the boundaries of the same address space. It couldn't shuttle messages to other containers like IDEs or EXEs. Let's talk about the distributed message broker idea. Typically, if you have two actors that need to reside in different containers like AEXE and BEXE, which can run on different computers or on the same computer, For each actor that needs to pair of actors that need to communicate, you create network proxies, which you start on the system startup. They establish TCP/IP connection, and then they shuttle messages back and forth. This is the typical scenario. I saw people do it, but this approach has multiple issues, and that's why I don't use it. First of all, it increases actor complexity because actors now need to manage their proxy code. It couples actors to proxy interfaces, and it makes those actors less mobile. It's harder to move them between the containers because they need to tag along their network proxies. So this adds complexity. And the question is, can we do better? And the answer is, yeah, we can if we use a properly designed distributed message broker. And the main three requirements for such a distributed message broker are: it needs to be 100% backward compatible with the local message broker, which means it needs to provide the same API and contract as the local message broker did. So you don't need to tweak the actor code involved for actors in this application. It needs to completely encapsulate inside the message broker the network proxies. So your actors don't need to create and manage their proxies. And it must support topic subscription, auto-healing, and auto-recovery when one or more of the containers go offline and then pop up back. Because in those containers, you need to maintain their connectivity. So this should be done by the distributed message broker. And the simple way to implement this, there is a simple way to implement this. This is a class diagram for the local message broker. You have the actors calling the abstract interface class that is implemented for a specific local message broker implementation. And in order to make it a distributed message broker, you extend the local message broker API. And the only thing you need is to redefine the subscribe and unsubscribe methods. Registering and unregistering publishers don't need to be changed when you transition to a distributed message broker. And then you implement extra functionality for forwarding messages via proxies managed by the distributed message broker, but you still can reuse a lot of code from already working local message broker. And when you call a constructor for the local message broker, it returns an object of this type. And when you do it for distributor, it returns the object of this type. That's all the difference. Now, let's look at how the message flow would change when you split a single container system into a distributed multi-container system. When two actors are in the same container, main UI actor calls local message broker and says, subscribe me to topic X. And actor B calls the same local message broker instance and says, register me to publish on topic X. And whenever it publishes a message on this topic, it is magically forwarded to the main GUI actor. Very simple. What happens when you split this thing into two containers, two separate address spaces? Each of them need to have a distributed message broker instance. The main GUI still calls its message broker instance, asking it to subscribe to topic X. On startup, message broker instances spawn gateways, one per connection between the two containers. The gateway actor forwards all subscription requests across the container boundary. Distribute and gateway actor on the remote side subscribes itself on behalf of this container to Topics-X messages, which would be published by actor B because it registers to publish the Topic-X. So when actor B publishes a Topics-X message, it goes to the gateway, gets transferred, forwarded to its gateway actor counterpart for the main GUI, and main GUI receives this message. All this complexity is handled by the distributed message broker. And as you can see, the main GUI actor and the actor B actor do not need to change because they're issuing the same calls. How easy is it to split a single container system into a multi-container system? It's quite easy. There are two steps that you need to do. The first step is instead of a local message broker object, you need to create a distributed message broker object. So that's just calling a different constructor. And the other one is you need to configure connection between the message gateways, which would be stored as distributed message broker settings in the INI file. And on startup, the distributed message broker takes in this file and spawns all the gateways configured here and starts waiting for connection. And in this example, this is part of the UI of a sample program. You can see that I have an established connection to myRIO target. Everything is green, but there is nothing running on the local host that I expect to connect to. So this is, I think, also pretty easy. Now, if you think that a message broker is a good match for your projects, this slide gives you a data point on whether to take an adventure of implementing one yourself, or maybe instead find a proven message broker, distributed message broker created by a reputable software development team, LabVIEW team. So I did this effort over 7 years, and it took me like 110 full-time days to do it in several sprints. The local message broker was created in 2015 and improved in the next 3 years. Then I implemented the distributed message broker and did some actor templates, which I use. Then I created the unit tests, which are extremely important part of this project. And then I did a benchmark application that I used to validate our message broker behavior. The code size is small. The local message broker is only 88 files, 58 methods, 8 classes, 2 after classes. Distributed message broker is about the same size. Actors are not part of my reuse library. You can use any actor design with this message broker, but just in case it's 3 classes with 33 methods. Well, not 7 methods, I'm sorry. This is the total amount of file, etc., etc. So you can use this as a data point to make your decision. And the last thing about the message brokers is the profiling application. I spent quite a lot of time on it because I wanted to verify that there are no bottlenecks in this architecture and implementation. First thing, there are no memory leaks when you run your actor systems for multiple days, and to measure the throughput of the system. In this example, I'm running a system consisting of 30 actors, 60 topics, 158 publishers, 170 subscribers, and with an average rate of 20,000 messages per second. 25% of the messages, this plot is the histogram of propagation delay of each message. For the 25% of delivered messages, they are delivered within half a millisecond. 75% are delivered within 1 millisecond. And this is running on a PC. This is Windows 10. It's not a real-time system, so things are running in the background. That's why you have such a big tail. And there were no memory leaks. And all this was done with a CPU load of between 40 and 50%. I wouldn't run an actor-based system that needs to exchange 20,000 messages per second on a single PC. I would probably break it. But that's the result, and it gives me assurances that my implementation works just fine. And now we get back, we got to a couple of examples. I did this myRIO monitor example as a proof of concept for context-agnostic actors, specifically to verify that the distributed message broker implementation is capable of running same actor sets without changes to their code in different deployment scenarios. And it's a very simple application. You have myRIO hardware. I think many of you are familiar with this. And it has a monitor GUI, monitor UI that runs always on the PC, and a data producer that is supposed to run on the RT side and talk to FPGA and push data to the PC side. It supports 4 deployment scenarios. You can run a simulated data producer on the PC side. You can run simulated data producer on RT side. You can run actual data producer on PC side talking to FPGA over a remote session. And you can actually run the actual message broker on RT talking directly to FPGA on the RT target. The reason to have these deployments is that on the real projects, these options can save you a lot of development time. We know that these days NI hardware lead times are unreasonably long. And we know that the monitor always runs on PC. And we can start developing the monitor code without having the actual hardware. We also know that FPGA development effort is about 10x. Takes about 10x more time than developing the same VI on the PC. So usually FPGA code gets later. And if you have different developers doing host side and FPGA side, usually the host side people are always waiting for the working bit file. So this also saves you time. The other thing is RT side development also takes more time, not 10x, but with LabVIEW IDE running on a PC, you have the immediacy, what Steve Watts called immediacy. This is a very important feature. You click the run button, and it runs. And you get your log files from your local disk and do other things really, really quick. On RT, you need to deploy your VIs, you need to compile them, you need to get your log files back from the RT target. This all takes time and makes your development experience less enjoyable. So the first scenario, deployment scenario, is you have a monitor UI running on a PC. You create a simulated data producer. You create a separate simulated data producer UI. I did it this way because I want to deploy this simulated DP to the RT target at some point, and it cannot run the UI on RT. And there is an actual data producer that talks to FPGA. And all four communicate. They don't communicate directly. They communicate through two topics, myRIO control and myRIO data. Commands go here, and data goes over this wire. So in this deployment scenario, you can create and debug your monitor GUI with the simulated data producer and make sure this pair works. And then you can take your simulated data producer, clone it, and build your actual FPGA data producer talking to FPGA. And you can run it on a PC using the remote session to verify that it talks to FPGA. And only then you need to switch to deploying to RT target. And this saves you time. I'm not a guru on RT development. I try to avoid projects that need RT targets. My preference is always to buy like a serial extension chassis and do custom real-time code on FPGA on that extension chassis and talk from the PC side to the extension chassis FPGA directly. This saves me time for development, and it saves me lead time on RT controllers and 4 or 5 grand for an RT controller, because a serial extension chassis used to be like between 700 and 800, and all days maybe they're around 1,000 now. So this is a time-saving example, and it shows that context-agnostic actors do work and have a good use. It is now like 47 minutes. I have one more example about message translation. I can skip it and take your questions, I think. You can always look up that translation example on the slides. And there is also a slide about the message broker. I use message broker since 2015. And during that time, only see a positive side of using them and no negative side. So you should consider whether you want to get one for yourself. And the last slide is when you use a message broker, you automatically get 4 flavors of actor decoupling. The first one is spatial decoupling. Publishers and subscribers do not need to know each other's locations in a distributed system. All the proxy code is managed by the distributed message broker. Temporal decoupling. Publishers do not need to be up and running for subscribers to issue subscription requests. This greatly simplifies initialization of actor-based system, especially if you split them into multiple containers. Synchronization decoupling, it's an obvious one. A subscriber doesn't need to listen to published messages because they get queued and they don't disappear in the void if subscriber is doing something else. And semantic decoupling provides means for message filtering and translation, and it allows you to use actors that were not intended to be used with each other. So that's pretty much it. And the take-home message is, you may want to boost your productivity by learning solid design principles and practicing them on your project. And you may want to future-proof your actor-based applications by building them on top of a message broker and by designing and using context-agnostic actors. Okay, that's pretty much it. I'm at 50 minutes, exactly the times I timed this offline. So now I can take your questions if you have any. I will publish this presentation on ani.com. I'll send a link to the Champions Forum and probably to the Actor Framework Forum. And you'll get a recording of this presentation on YouTube. Just look where the GLA Summit will put it. Well, that's pretty much it. Thanks for sitting through this presentation. I hope you enjoy it, and I hope you'll make the right decisions next time you start developing a distributed system. That's it.